Welcome to the Explainer. Okay, let's just jump right into this. Today, we're looking at a totally thrilling, super high-stakes process that basically governs almost every piece of modern tech you touch. We're talking about the microscopic hardware inside your phones, your computers, your cars, and specifically how it's actually reliably manufactured through a process called VLSI, or Very Large-Scale Integration. Taking a complex chip design from just a simple idea to physical silicon is a massive milestone in the semiconductor world. It requires this precise, almost zero-tolerance coordination of engineering disciplines. It's intense, it's ridiculously complex, and the pressure to get it absolutely perfect on the very first try is just unbelievable. To really get why this VLSI process is so incredibly rigorous, we have to talk about the sheer stakes involved. Unlike software, right, where a developer can just push an over-the-air update if there's a glitch on your phone, hardware is permanent. If a single hardware bug is found after that chip is manufactured, it can literally cost millions of dollars and cause these massive cascading delays. Months of them. Everything just grinds to an absolute halt. You can't just patch physical silicon. It's kind of like trying to rewrite a book after millions of copies have already been printed, bound, and shipped all over the world. No way. So this terrifying, irreversible reality, that dictates everything we're about to look at today. So here's our roadmap for today's explainer. 1. The million-dollar bug. 2. The 6-step VLSI flow. 3. The gatekeeper of quality. 4. How DV engineers work. 5. Builders versus breakers. And finally, 6. Achieving coverage closure. All right, moving right along to Section 2, the 6-step VLSI flow. So there's this really rigorous 6-phase timeline a chip actually has to survive to become a reality. Phase 1 is spec and architecture. That's defining what the chip needs to do and aligning it with PPA, power, performance, and area goals. Then Phase 2 is RTL design, where they translate that architecture into code using specialized languages like Verilog or VHDL. Next up, we hit Phase 3, synthesis. Here, the RTL code is frozen and synthesized into a gate-level netlist, basically a massive, super detailed digital schematic, all while applying strict timing and power constraints. Phase 4 is physical design, turning that logical schematic into an actual physical layout, floor planning, synthesizing a clock tree to distribute timing signals, and routing millions of tiny transistors. Phase 5 is sign-off, which is all about those non-negotiable geometric and electrical checks. And finally, Phase 6. Tape out. Now, tape out demands some special attention because of its sheer gravity. This is the final step where the design database, usually in this GDSII format, which is basically the ultimate geometric blueprint of the chip, is sent to the foundry for actual fabrication. Tape out is, well, it's the absolute point of no return for the design team. Once those files are transmitted, those millions of dollars we talked about, they're fully committed. You absolutely cannot go back. So everything leading up to this exact moment is intense, highly scrutinized, and painstakingly double-checked. Okay, Section 3, the gatekeeper of quality. What's truly mind-blowing about this whole process is the incredible weight the verification team carries. Up to 65 to 70% of the total design cycle is dedicated purely to verification. I mean, just think about that staggering proportion for a second. The vast majority of the time, the effort, the money spent making a new microchip, it isn't actually spent designing it. It's spent verifying that the design works perfectly. Their whole role is to act as the gatekeeper of quality, ensuring that the RTL code perfectly matches the architectural specification before the design ever moves to expensive physical implementation. These engineers are the ultimate safety net. Their entire existence in this VLSI flow is dedicated to finding flaws and preventing that catastrophic million-dollar post-manufacturing bug from ever seeing the light of day. Which brings us to Section 4, how DV engineers work. The verification methodology basically breaks down into 4 distinct, highly controlled steps. Step 1 is verification planning. Before writing a single line of code, they intensely analyze the specs to identify potential failure points and create a comprehensive feature list. Step 2 is test bench development. This is where they build a sophisticated environment around the design, a virtual world where the chip can be safely tested, using universal verification methodology to code drivers and monitors. Then, step 3 is stimulus generation. This is how they actually feed data into the design. They'll throw everything at it, from expected normal data to complete digital garbage, just to see how it reacts. And finally, step 4, checking assertions. That means writing strict, specific rules to instantly catch any protocol violations during the testing. Let's look a bit closer at that stimulus generation step. Because it relies on this really fascinating concept called constrained random verification, or CRV. Instead of testing just one predictable scenario at a time, DV engineers write sequences that generate random data within valid ranges. It's kind of like, well, think of it like handing a video game controller to a toddler, right? They'll just press chaotic combinations of buttons you'd never logically think of. The engineers are purposely hunting for those unpredictable corner cases that a normal human tester would just completely miss. They throw chaotic but technically valid data at the virtual chip purely to see if it breaks under the pressure. And, if throwing random chaotic data at the design isn't enough, they double-check everything with pure math. Formal verification uses mathematical proofs to guarantee the design can never, ever enter an illegal state. They literally leave nothing to chance here. They aren't just running simulations to see what happens over time, they're actually using rigorous algebra to mathematically prove the foundational integrity of the design. It's definitive, irrefutable proof that the logic holds up. Moving on to Section 5, Builders versus Breakers. There's this fascinating psychological divide in mindset here. The RTL design engineer has a very constructive, architecture-focused mindset. Their whole focus is on how to implement the logic, creating the exact Verilog or VHDL code that literally becomes the chip. Think of them as someone painstakingly building an intricate Lego castle. The DV engineer, on the other hand, operates with a beautifully destructive, audit-focused mindset. Their focus is solely on how to break that logic. Their output is the UVM code that actively tries to tear that Lego castle down to find its weak points. It's this structured, ongoing battle between creation and destruction. So the really interesting part is how each side essentially defines a win. For the builder, the RTL designer, success means the design tightly meets the power, performance, and area goals. Making sure the final chip will be blazing fast, physically small, and highly battery efficient. But for the breaker, the DV engineer, success has absolutely nothing to do with those optimizations. Actually, scratch that. They don't care about optimizations at all. They are only satisfied when the design is rigorously proven to be bug-free and 100% covered by their tests. Which begs the absolute crucial question. Section 6, Achieving Coverage Closure. How do we actually know when this massive auditing process is finished? The definitive answer is coverage closure. A verification engineer doesn't just stop because a few test simulations pass. Oh no, they stop only when 3 incredibly strict exit criteria are met. First, code coverage. They have to definitively prove that every single line of RTL code, which can easily be millions of lines, was executed during simulation. Second, functional coverage. They have to ensure every single feature, edge case, and combination defined in their verification plan was fully exercised. And third, strict bug tracking to verify that all found issues have actual working fixes. They only put down their tools when they have systematically proven they've tested the whole shebang. Now, pulling off this multi-million-dollar defense strategy requires a highly specialized, intensely technical arsenal of skills. DV engineers have to master the system Verilog language, which is the core industry standard. They need deep expertise in complex methodologies for system-level verification and fluency in running heavy-duty simulators. And on top of all that, they need deep domain knowledge of specific protocols like AMBA, PCIe, or DDR, essentially the high-speed digital highways that let different parts of a computer seamlessly talk to each other. It's a monumental, often hidden effort that makes our entire modern digital world possible. Which leaves us with this final thought. If up to 70% of the entire chip design cycle is dedicated solely to finding flaws, running math proofs, and trying to absolutely break the design before it reaches that point of no return, what invisible bugs do you think might still be lurking in the microscopic hardware you rely on every single day? It certainly makes you look at the phone in your pocket just a little bit differently, doesn't it? Thanks for joining me on this explainer, and I really hope this sparked your curiosity to learn more about the incredible, high-stakes world of VLSI design.